All right.
Tangent equals square root of 3. And then it's given that first block of opposite of 60 degrees, or like, what was it, pi over.
Well, hopefully it will come up. I had some trouble getting it on the screen last time. I hope I don't have to go through all that again. Just work this time. Come on. You can do it. I'm always referencing the Olympics, where we were all supposed to applaud the old man, who it turns out was turning a blind eye to all kinds of abuse on the girls. But whatever, it's for sports, right? So and then, but he this poor girl already half broken her ankle or whatever, and then he's like, "Run, do it! You can do it! You can break your ankle for the masses, all right?" I always remember that. You can do it. Anyway.
Left it as sine 4x plus x. Are we okay?
40. If you left it as sine of 41x plus x, yeah, that's okay. I give you half credit for that, but no, I'm kidding. Give you most of the credit for that. Let's see here. So problem 2. Yowzers. That's very hard. Make sure we can. For problem 2 here, this is a law of sines problem, and so if I can zoom in a bit. Sorry about the rainbow effect here. I don't know how to stop that, but anyway, here we go. So, of course, the law of sines says the sine of the angle over the length of the side opposite is a constant for all 3 sides. And so you have this equation, well, 2 equations, really, 3 equations. And so all I do is just solve for B and solve for C, and I get that. So 13.23 and 14.96. Then this one, like I said, use the law of cosines. So the picture is something like this. That was supposed to be a line, but that's about all I got right now. So there it is. Sorry about that. And so here A is 2, B is 3. That's why I've got 4 and 9 and minus 12 cosine 110. So there you go, 17.1. So the law of cosines is useful when we find ourselves outside the province of right triangle trigonometry. So I felt like I told you guys during the quiz, I added these 2 problems because I realized that technically speaking in the course planner, these 2 topics, law of sines and law of cosines, were after test 2, but that's not accurate because we, of course, have covered them. I spent considerable class time proving these things, right? So I would like it to be on test 2 because that's the appropriate place for it in this course as I've taught it. So I wanted to warn you about that because I haven't actually assigned additional homeworks on laws of sine and cosine, right? So I wanted to let you know I might want to test on it. And if I do test on it, it's very likely that my test question would be somewhat in line with the way I did it here. All right? Yep.
That number.
Now, it is possible I've miscalculated something. What'd you get?
So when I do 13 minus 12 cosine 110.
Are you in degree mode?
Yeah.
Curses. Well.
Was I not supposed to be in?
You are supposed to be in degree mode. The question is, was I?
Because when I do 13, I get that as 17.10, and then I have to square root that 17.10 to that.
This is really fussy because cosine of 110 is, I'm in radians. Never mind. What was I just telling you? You need both in this quiz, right? So I had to go back and forth. But cosine 110, I'll recalculate it here. Cosine 110 is minus 0.34. Okay, so I multiply that by minus 12. I get 4.104, add 13. Oh yeah, that was the thing I should take the square root of. So the answer should be the square root. I don't know how, I got lost in the calculation. This is wrong. right? It's supposed to be the square root of 17.10. I did, honestly, when I was doing the solution before class today, I did think that number looked a little bit odd. So yeah, I should have 4.136 here. 4.136. So I'll go fix that and rescan the solution. By the time you see it in Blackboard, it'll be changed. That won't happen until Friday because I'm giving people missing until Friday to do it, Friday morning. But then Friday I'm posting this video. Yeah. So, and then I also told them we're moving the test to Monday. So, okay, so how about problem 4? Yeah, so like I was saying, you could just graph tangent, graph y equals the square root of 3 and look for points of intersection, right? That just gives you the big picture. Then you should use your knowledge about special angles to like fine tune it. So the first one is going to give you pi over 3. See, because pi over 3 is, so like the sine of pi over 3 is root 3 over 2. The cosine of pi over 3 is a half. So when you divide those things, the halves cancel, and you're left with like root 3. So tangent of pi over 3 is root 3. Tangent of pi over 6 is 1 over root 3. For just almost the same reasons, but the sine and cosine being flipped. So, that's the kind of knowledge I'd be familiar with as I'm teaching trigonometry, but I would typically kind of lose as I get away from this course. But hopefully you'll know more about trigonometry in this semester than you ever will any other time in your life. Unless you teach trigonometry, and then you'll learn lots more. But anyway, so yeah, I got pi over 3 and 4 pi over 3. I think it's useful and healthy for us to just take a second to look at Desmos. This is Desmos. So Desmos, you can put like y equals tangent x, and if you use curly brackets, you can condition it. You can limit the graph to just look at a particular spot. And I don't know if my camera is successful, and I'm zooming in, see if I can. So there are my inputs. And the result, obviously you can't use this on the test, right? But if you have homework and you're trying to like think through things, or maybe you're doing trigonometry in your job later, or whatever, this is a very useful resource because actually it automatically kind of homes in on intersections of different things. And if you hover your mouse over that, it'll actually tell you that this is pi over 3, comma 1.732, which is square root of 3, and 4 pi over 3. So like, in terms of like checking homework and stuff, this is another resource you might consider using. It's free, so you can't exploit them. All right, in fact, using them is already like the highest form of praise for them, right? They just want people to use the product because it's a good product, and I'm sure various government grants have probably funded it. Or just people with time on their hands. Actually, I don't know. I haven't looked into the history of Desmos. I don't know where it comes from. Now, the problem I had originally signed was secant cubed plus tangent squared secant, and I worked that problem out, and I was like, this is not interesting. Like, after I simplified it, it was still the same ugliness. So I thought, if I change this problem to secant cubed minus secant, then I can actually illustrate a simplification. And so, yeah, if you do that, you can factor out a secant. You get secant squared minus 1, but that's tangent squared. So in my view, secant x tangent squared x is a simplification. Now, even if you just factored out a secant x here, I will give you partial credit. Like, to me, that's the first step. But that would be like halfway.
What?
Yeah?
Ours said secant squared x minus secant.
Yeah. Secant cubed x minus secant, yeah. That was the one on top. Solution's up on the top. This is the quote-unquote solution to the one I originally printed, but I bailed on, and I whited out on your test, on your quiz. You see, I whited out tangent squared and drew in a minus.
I'm looking at the top, I'm trying to figure out how it works.
I just factor secant out, then you have secant squared minus 1. But secant squared minus 1 is tangent squared. That's it. Yeah. Secant tangent squared. Yep. So like if you were integrating secant cubed minus secant, this would actually be very, very useful because it would, oh, well, let me not oversell it. I'll go on. So this one, I need to put everything in terms of sine, otherwise I can't solve it, yeah? So convert the cosine squared to sine squared minus 1. Actually, that's minus cosine squared. I put the minus into here. And then that gives you this quadratic, which factors like so. And then by the graph, you can see there's one solution for the one case, and there are two solutions for the other, right? For a half, you can either get it at pi over 6, right, or pi minus pi over 6, which is 5 pi over 6 over here. And we only hit 1 at pi over 2 in the 0 to 2 pi cycle. So them's your three solutions there. Close is better than nothing. Let's see here. And then for this one, I thought, I think I solved this in class, this kind of problem in class, by looking at the graph of secant. And I thought to myself, that's dumb. I should prefer to look at the graph of cosine. So I traded the problem 1 over secant squared for 1 over cosine squared, which gives me flippity-floppity cosine squared equals 1/4, and then plus or minus a half, of course, taking the square root of both sides is what I have to face. But I limited the discussion here because I'm so tired of everything being 0 to 2 pi, so I made it 0 to pi for a change. And so 0 to pi, this is half of the cosine graph, yeah, that's it. And so there's only one place where you hit a half, and there's only one place where you hit minus a half. And I think you could have used your calculator to find both this and that in this context. So, actually, problem 7 is a very friendly problem.
Could you use tangent as well, like where you convert it to 1 plus tangent squared?
Oh. So you solve tangent squared theta. Wait a minute, no.
So I converted, I switched,
Just a second. I got to think about how to switch secant squared to tangent squared.
it's in our identities.
Yeah, I agree with you. Secant squared is tangent squared plus 1. Okay, so you looked at tangent squared equals to 3?
Yes, that's square root of 3.
And so tangent's plus or minus root 3? Yeah. That would have been a legit way to do this. You should have got the same answer. Nice. Yeah.
It was pi 3.
I think my way is lazier, though. But yes.
Yours deals with more fractions.
Yeah. But it's all good. I just, sometimes I just tackle the problem straight on like in class. But maybe there's a better way sometimes, yeah. But anyway, that's it for today, guys. Have a, I'd say have a good weekend, but that doesn't seem accurate.